So, hello everybody. Welcome to this webinar organized by the IEEE Egypt Sensor chapter. I hope that you can hear me well. This is Samah Abdul Latif, the IEEE Egypt Sensor chapter counselor, secretary. And I am here today to operate our fifth webinar to be implemented this year. Fortunately, today we choose to have a theme or a topic under the AI or the artificial intelligence utilization in sensing application. And fortunately, again, we have two esteemed, prestigious speakers to be with us today during about 1.5 hours, starting from now, to operate very interesting presentations. We have today two speakers. We have Professor Owais, civil engineer, a professor of civil engineer in Asyut University, and we have Dr. Mandal. So I will start first, if you permit me, with giving a short introduction about the first talk. So our first speaker today will be, as I mentioned, Professor Mahmoud Owais. Professor Mahmoud Owais is a professor of highways and traffic engineering, faculty of engineering at Asyut University. The talk today will be labeled or titled by Machine Learning Powered Sensing Deep Learning for Optimized Traffic Sensor Placement and O/D Flow Estimation. Professor Owais is our distinguished speaker for today with more than 40 published paper and 1.2K citations. Professor Owais conducted more than 750 reviews with top journals, including IEEE Transactions. Professor Owais also is acting as an associate editor at Springer's Innovation Infrastructure Solution Journal. And finally, Professor Owais is a member of the Egyptian Code Review Board for Highways and Traffic Engineering. So I think now the floor will be, I will stop sharing from my side, and I will allow Professor Owais now to start sharing his presentation and to start his talk. Professor Owais, I think you can now start unmute your
Thank
mic.
you. Thank you.
Yeah, and you can start your presentation. As I mentioned,
Okay.
we have 45 minutes overall. Professor Owais will consume about 40 minutes for his presentation, followed by 5 minutes for question and answer. I would appreciate if you have any question, just to write it on the chat window. Professor Owais will do his best in order to answer as much as possible questions during or by the end of his presentation. And then the more or the questions that will not be answered, we are going to send it to Professor Owais via email, and he will kindly reply to this question. So please don't interrupt Professor Owais for the next 40 minutes, and looking forward for an interesting presentation. Thank you, Professor Owais. The floor is yours.
Good evening, everyone. It's my pleasure to present on deep learning for optimized traffic sensor placement and OD flow estimation. I'd like to thank IEEE Sensor Council Egypt chapter for organizing this webinar and inviting me to share my work. Today, we are solving two key problems in traffic management. The first problem is origin destination estimation problem. The second is optimal traffic sensor location for accurate OT flow prediction. I know most of audience don't have much background on transportation science, so I'll try to illustrate key concepts and terminology related to transportation science during my presentation. Let's begin with the first problem. Simply, origin destination is about figuring out how many people or vehicles travel between 2 points in transportation network. Technically, it refers to the process of estimating the flow of traffic or travelers between pairs of origin and destination. The point where the trips start, we called it origin. The point where the trips or travelers end at is called destination. So the problem knowing the number of a certain OD, like the people travel from El Maati to El Zamal. For a transportation network, all the points we need to know the interrelated trips between different points in our transportation network. Before we begin to know how this problem is complex, what we bother ourselves to estimate the OT matrix for a transportation network. This is a cornerstone in traffic management. It helps us for traffic flow analysis. It is essential for understanding and predicting traffic patterns. It also affects our infrastructure planning. It guides decision on route and transit network expansions. It also used for optimizing our resource, helps to allocate control resources efficiently. It's used for performance evaluation. If we have different projects in transportation, knowing the OD metrics helps us to evaluate the effectiveness of transportation projects and choose the most economic one. It's used also for congestion pricing and tool management. It's also used in safety analysis to identify high demand areas needing safety improvement, and also for incident management to predict and mitigate the impact of accidents on our network, and how to reroute routes based on our estimated OD matrix. To know how this problem is complex, let's imagine we have a study area as shown. We want the first step to determine the OD matrix is to divide it into zones. The size of zone or how to divide it isn't our concern today. Let's imagine we managed to divide the study area into 8 zones as shown. For each zone, we will determine a point called a centroid. This centroid for zone is our O or D. When the trips started from it, it is O, origin. When trips into it, is D. All the trips of the zone, we will assume it will be allocated to the zone centroid. Therefore, for the study area, people tend to move out of their zones due to the socio-economic or land uses. Some people want to travel from residential area to non-residential zone to go school, work, commercials. So for each zone, we'll have trip production, total number going out of the zone, like the table on the left, total production for the 8 zones, or the attractions for the 8 zones, total number of trips going into the zone. The trips going for out zones will distribute among the different zones. For example, trips going out from zone 1, some of it will go to zone 8 from residential area, as we said, to non-residential area. And after that, the number of trips going from 1 to 8 will return from 8 to 1, and so on. So we will have, for this study area, we can arrange these trips in a matrix. The 8 zones will be our rows. The 8 zones will be our columns. Each cell represents the trips going from zone to another zone. Like this cell, it is the number of trips going out of 2, going to zone 1. Our objective in this first problem is to knowing all these trips number for our study area. Is this problem easy? Unfortunately not. It is very complex. To know its complexity, let's assume we have already known OD matrix. We managed by somehow to obtain this OD matrix. Now, what is the product of this OD matrix? It is the flow on the links, the streets on the network. The people moving from 2 to 1 will use the transportation network to move. So they will use the streets. When we assign all the metrics, we will get the flows on the network. This is a simple representation for the transportation networks. The lines represent the streets. The nodes represent the intersections in the network. The blue lines represent the flow after the assignment. The thickness represents the volume of the flow. With increased thickness, we know that from this assignment, there is a much larger flow on that link. Is the traffic assignment itself simple problem? No, it is also complex problem. Why? Because trips going from one zone to another, there is in a network many routes to go. Let's assume there is someone wanted to go from 6 to 4. He can go straight from 6, 1 to 4. He can also go to 6, 7, 11, 1 to 4, and so on. You will, for this toy network, can generate a lot of routes to connect 6 with 4. In larger networks, there is countless routes connecting each OD pair, origin and destination. How people move on the network and choose their routes. We will reach to the most famous assumption in transportation, which is called user equilibrium. The user equilibrium states that in transportation network, travelers will choose routes such no one can reduce his travel time by switching routes, and we can say we reach the user equilibrium state. Let's imagine we have a certain OD pair as shown. There is 3 routes, for example, connecting them. The people tend to use the shortest path in time, so they will take the route 1. We assume this is the shortest path. After after a while, when all people select this path, the travel time of there will be congestion, so the travel time of this path will increase. So some people will tend to move to the second larger route, which is route 2. Then when route 1 and route 2 become the same travel time, we reach the equilibrium. Route 3 doesn't have any flow on it because it is after equilibrium is larger in time. So all used routes are minimum and equal. Any unused route is much larger in time, so it will be used by the user, and no one find a benefit to change his route and select another route. So we reach equilibrium. In this simple network, equilibrium is easy to calculate because we have single OD. But in a real network, we have many OD pairs. So each route, when we estimate travel time on a route, it is not just about the route in isolation. It depends on how many vehicles from all OD pairs are using the same length. Links are common in many routes. So this creates a kind of interdependence. If one OD pair shifts traffic onto a certain corridor, the travel time for the other OD pairs using that corridor immediately changes. So travel time estimation is not static, it evolves dynamically as the assignment of flows across the whole network changes. In practice terms, this means we can't assign each OD pair independently. Instead, we need an iterative system-wide process where every update in one OD flow requires recalculating times for all others. That's why the complexity grew quickly. The more OD pairs and the denser network, the harder it becomes to pin down accurate travel times. Fortunately, in literature, we have many methods to convert the OD matrix into traffic flows on the network, like variational inequality optimization problems, fixed point problems, heuristics, recursive algorithms, and simulation tools. Now, the question, what we have in real situation? In real situation, we have the product of assignment. We have flows on the network. We have the cars on the streets. We can count them, so we can know the flows on the streets. Is the problem reversible? If we know the flow in the street, can we go backwards to know the real OD matrix that produced these flows? Unfortunately, not, because this problem undetermined. Why it is undetermined? Because many OD pairs can produce the same link flows we observed. So we can't determine which one is the true unknown OD matrix. In literature, some attempts try to estimate this OD matrix from counts in streets. The counts in streets is the product of is the data of traffic sensors commonly, the methods like least square estimation, maximum likelihood estimation, entropy maximization, Bayesian networks, linear programming, heuristics, and meta-heuristics. The select of method depends on the available data, required accuracy, computational resources, but all these methods has common assumptions that you have a prior OD matrix, a historic one, not accurate one, and you need to update it by these statistical methods. to the time of my work, there is no attempt to use machine learning for this direct OD estimation problem. This is because a lot of reasons. Some of it that the main problem is the limited data. In many cases, only partial traffic data. We can't provide sensor on the network on all the network links, as we will see in the second problem, traffic sensor location problem. And while the full OD matrix remain unknown, machine learning typically require large amount of accurate training data to learn meaningful patterns. And as we said, we have one prior OD matrix. How we can learn machine learning by one OD matrix, which is not accurate as well. This because can be difficult to obtain for every origin destination pair on a network. Also, the non-linear relationship among the traffic flows and the OD pairs is highly non-linear and dynamic. Machine learning models need to capture these complex relationships, but traditional models may struggle to do so without significant customization. Also, the black box nature of machine learning. Many machine learning models, especially deep learning models, are considered black boxes because they lack transparency in how decisions are made. This is problematic for OD estimation, where it is crucial to understand how model drives its estimates, especially when critical decisions like sensor placement depend on these models. So we can't know in advance what links drive the accuracy of the estimated OD matrix. This leads us to the second problem, which is traffic sensor location problem. The traffic sensor location problem, or for short DSLP, I will use this shortcut for the rest of the presentation. TSLP stands for traffic sensor location problem, involves determining the optimal location for deploying traffic sensor within a transportation network to collect accurate traffic data such as flow, speed, volume with minimal cost. The goal is to place a limited number of sensors in a strategic location to maximize the accuracy of traffic flow estimation, such origin destination, our first problem today, while considering factors like sensor cost, network coverage, and sensor reliability. Our second problem, is it a simple problem? Unfortunately not. It is also a complex problem. This because the shared space of this problem is combinatorial. It is dependent in factorial of number of links. So the problem search space complexity explodes with the size of the network. In addition to other dimension of complexity, as it is multi-objective, because deploying sensors as a network, it is a multi-objective because you search for accuracy and cost, two objectives. It is also proved to, in many forms, to be NP-hard, non-deterministic polynomial solution algorithm. Also, there is a dimension we will talk about today, that sensor D may be failed or give inaccurate counts of traffic flows. For DSLP in general, there are many objectives to distribute your sensor on a transportation network. The first, and we were talking about today, is the OD estimation matrix or updating. We know we have a prior one and we want to update it. For short, OD estimation problem. Also, there is flow observability, link flow inference, path reconstruction, screen line or traffic surveillance problem, and travel estimation problem. For TSLP for OD formulation can be represented by this mathematical formulation. It has two components, multi-objective. The first component reduces the error, the deviation between the true unknown matrix and the estimated one. We want our estimation is more close to the unknown OD. The second objective is the cost of sensor deploying. We want to minimize the number of sensors to network to obtain the maximum accuracy. So our decision variable that is integer decision variable 0 if you not select this link to deploy your sensor, 1 if you select this link to be equipped with your sensor. TSLB has many methods in literature for solution, like linear programming, integer programming. We see that we have integer variable 0 and 1, mixed integer linear programming. There is also methods that depends on graph theory. These are the exact methods. There are some heuristics and meta-heuristics methods are commonly used, like greedy algorithms, genetic algorithms, simulated annealing, practical swarm optimization. There is also challenges for using machine learning for this problem. Before my article, there was no attempt to solve the TSLB for the ODEB by machine learning, as there was no analytical concept that machine learning can be used in such integer optimization problem. There is no method to use machine learning which depends on input and output data to solve this integer minimization problem. So we see two problems. The first problem is so complex. The second problem is too complex. Literature always separate between them. Some they are tackled separately. There is no attempt to integrate them in one general solution because each one is very complex. So I tried to develop a general framework to solve these problems as they related, because good distribution of traffic sensor will result in accurate OD matrix. So I believe from highly complex problems, each solution often emerge. Before we go to our developed framework, we want to know what our input, what our output, how these two problems related to the input and output. In the input, we have, or for our case, the output, we have three terms for the OD matrix. The first one is the reference OD matrix, the prior OD matrix, which come from historical data in our network. The second one is the estimated OD matrix. It is the matrix resulted from your method. The third one is the true OD matrix, which all transportation engineers don't know for any network. Till now, there is no method to ensure that your estimated OD matrix is the true one. All these metrics can be applied to assignment model to result in traffic flow. The reference OD matrix will result in prior OD flows, historical flows on the network. The estimated will result to estimated flow. The true OD matrix will result to the observed flow by traffic sensors. So traffic sensor counts will give us this input. So traffic sensor counts should depend on the two, the observed and the prior flow. So our target is to reverse this problem, because we want from this observed flow to return backward to get the true OD matrix. Truly, we get the estimated, but we want that the estimated OD matrix become more close to the true OD matrix. This simplification to the proposed framework. The framework depends on four main steps. The first step is Monte Carlo simulation. The second step is the selected assignment model. The third step is the selected machine learning, which is stacked autoencoder deep learning. The fourth step is the global sensitivity analysis tool. How these four steps work in this framework? First, we go to Monte Carlo simulation, which depends in synthetic input data generation. We have the prior OD matrix. We know the means of, we consider this prior OD matrix, the mean of the OD pairs. First, we will want to we want to deal with a matrix. We'll convert this matrix to a vector. We will arrange all these cells in one vector, T, and we have the total demand. We can we can sum all these prior OD matrix values to get the total demand. Then we will get a factor randomized of size T. So F will be generated randomly and distribute this T to obtain a simulated OD vector. This if as generated in one vector, so it makes the T values correlated. So we add also an independent random variable to represent the random change in the OD pairs from the interaction between the OD pairs. So we have a factor represent the independence of OD pairs flows, and we have a factor for independent OD flows. After we conduct Monte Carlo simulation, we have a large number of OD matrices. The second step is to apply your assignment model. We selected an assignment model based on equilibrium. The method of solving this assignment model is called the method of successive averages. This is the mathematical formulation, and this is the algorithm of how solving it. It depends on three main steps. You calculate your path's travel time, find your shortest path, assign the shortest path, then adjust the path's choice toward equilibrium. Then you will have a new travel times and do the loop till you reach the equilibrium state, as all flows, all paths are minimum and no one can benefit from changing his route. So now we have a large number of ODs. We managed to apply assignment model to get a large number of corresponding link flows. So we can go to machine learning. We have input and output. What our input here is the link flows. What are the output he will learn is the target OD matrix. So we used a deep neural network with autoencoders. The select of such machine learning is due many reasons. The first one is the dimensionality reduction for traffic data. Traffic flow data across, as we said, across multiple links in a network can be highly dimensional and spaced. And autoencoders can compress this high dimensional traffic data into a lower dimension, latent space, while retaining essential features such as traffic patterns, traffic demand fluctuation, and network topology. This can make the problem of sensor location more manageable by reducing the complexity of data. The second reason is learning latent features. Autoencoders can help extract latent features that represent traffic flow dynamics and their relationship with OD demand. By learning these features from traffic flow data, autoencoders can provide a compact and informative representation of the network that can be used to predict OD flows with fewer sensors. The third one is reconstructing missing or incomplete data. In the TSLP, some traffic sensor data may be missing, or we can't distribute our sensors in all the links because the budget constraints. Autoencoders, especially the denoising autoencoders, can be used to reconstruct missing or noisy data from the available sensor reading. This improves the accuracy of OD estimation even when the network coverage is limited. As we said, we can distribute our sensor on all links on the network. Some networks has 5,000 links. We can buy 5,000 sensors and to get a sensor on each link. Also, improving sensor placement efficiency, autoencoders can help to identify which links in a network contribute the most to estimating the OD matrix by learning which sensor placement are most informative based on their latent features. Autoencoders can guide the optimal sensor placement strategy, ensuring that sensor deployment in locations that maximize the accuracy of OD estimation while minimizing costs. Now, we trained our machine learning and it get high accuracy. We can input, introduce link flows and get the corresponding OD matrix. In the training, we don't which links is important. So when we apply the assignment model, we have all length flows. So we'll begin train with all length flows. In reality, we want to deploy sensors in some length on the network. So with the obtained accuracy, we want to know which length determines this accuracy. After training machine learning, as we said, this problem, it is a black box. We put link flows, get the OD pair, but we don't know which links in advance determine our accuracy. So we can know this by sensitivity analysis. There is a sensitivity analysis, the rotational sensitivity analysis, which depends on changing one variable around the mean when fixing the remaining variables, input variables, into their mean. This is a problematic because fixing on the mean and representing doesn't capture the interaction between each capture the interrelation between the input variables themselves and our target output. So we will go for global sensitivity analysis, which depend in varying all the input variables at the same time and not around the mean, but around the whole domain of each input variable. And we can capture the sensitivity by tracking the variance of our bot. So the method selected is called variance-based sensitivity analysis, which assumes that the variance of our bot is decomposed to the first order variances. So for the data, we select one input variable, say xi represent for the first input, second input, which each input in our problem is a link flow. The first link, the second link, to study its sensitivity to the output, the accuracy of our OD. So we have generated random data. So we have the scatter plot. We want a quantitative scale, which is sensitivity analysis index, to know is it important or to rank it with the other input. So to think of the horizontal axis as one input variable, as we said, and the vertical axis is the model output, which is the accuracy of our OD now. Each blue point is one simulation. We have made a large number of simulations. Now, if you look at the pink points, they represent the average output when the input take a certain value. We take the averages at each certain value. If those pink average change a lot as the input moves to the left or the right, it means this input strongly influence the output. The sensitivity index is then computed as the variance of those pink averages. The bigger that the variance, the more important this input in explaining the output variability. So we can do this for our all input variables, so we can rank them and know which links is important to deploy sensors, which links is negligible, we can't not deploy sensor on them. In in the work, I selected two networks. The first network is medium real size network, which consists of 76 links and 182 OD pairs and 24 nodes. And it is a common benchmark in the TSLP problems called SOX4 network. I conduct the whole framework to in this network, and I calculated sensitivity index for all the 76 links. The figure shows not all the rods in the network are equally important. We see some are high in sensitivity, some are small, and this helps us to understand the travel demand. A few critical links stand out with much higher sensitivity. We can select them to deploy our sensors, and the low sensitivity values can be neglected in the deployment our deployment strategy. So we can go for this figure to draw the error with the number of used links. We see the trade-off between the number of sensors installed and the accuracy of demand estimation. As more sensors added, the error in predicting audio flows steadily decreased, but after a certain time or point, improvement become marginal, showing that high accuracy can be achieved with only a limited number of sensor-based sensor, making it practical guide for balancing cost and performance. This can be like a Pareto optimal solutions. The second network is a large synthetically generated network with 900 node grid network was constructed. It has 3,480 links with 900 nodes and approximately 1 million node pair. We managed to get a high accuracy in estimating our OD matrix. We have a lot of link flows and a lot of corresponding OD matrix. We have 80% for learning and 20% for testing. We managed to get accuracy of 90 of R square 0.9 for the testing data. So it reflects the efficiency of our proposed framework. I believe that I was very quick. I'll take less time. Okay, we reached to conclusion. We see that we proposed the integrated framework and introduced a novel deep learning-based architecture using a stacked autoencoder coupled with global sensitivity analysis to simultaneously solve the two stated problems, OD estimation problem and traffic sensor location problem. We managed to reverse the complicated traffic assignment problem. We demonstrate the ability to estimate OD flows from limited link flows data, effectively reversing the conventional traffic assignment process. We managed to solve the TSLP by sensor prioritization, applied global sensitivity analysis to identify the most influential links for accurate OD estimation, enabling cost-effective and optimized sensor placement. We managed to use scientifically data training developed by Monte Carlo simulation to overcome the lack of large-scale historical dataset, ensuring a robust modeling training. We managed to get a high accuracy on a benchmark network and also a large network, achieving root mean square and high accuracy exceed 90% in both medium scale 6 folds and large scale 900 node network. We managed to obtain Pareto optimal solution, producing a spectrum of solution balancing estimation between accuracy and essential budget constraints, supporting flexible decision making. There is a trend for future work. We can incorporate measurement noisy and sensor failure into the estimation process to enhance robustness for real deployments. Extend the framework to handle time varying OD flows and the temporal sensor data for real time traffic management. Adapt the method to work with multimodal and heterogeneous sensors like video lidar, AVI, with varying accuracy and cost. Optimize model architecture and training to improve computational efficiency for ultra large urban networks. Combine deep learning with Bayesian or probabilistic graphical models to improve interpretability and uncertainty quantification. Conduct real-world pilot study to validate performance under operational traffic condition and diverse network topologies. Any questions?
Thank you very much, Professor Owais, for such a nice presentation. It was really a nice one. So if any of our respected audience have a question, I would appreciate if you can just raise your hand. Let me start. We already have a question in the chatting area for Dr. Ahmed Ali. I think if Dr. Ahmed Ali is here and he would like to make it by himself, please go ahead. Otherwise, I can make it on his behalf? So
I
let me
used
go.
the I used the I
Yeah.
used the
Mm,
synthetic OD data. My method depends on synthetic OD data generation
mhm,
by Monte Carlo.
mhm,
Transfer learning, it can be transfer. Each network need to be trained by itself because each network has its own characteristics and driver behavior and driver selections. We can transfer learning from a network to another network. This is for sure. Yeah, it can be even in future.
that's great. So do we have any other question? Okay, so in this case, if you permit me, Professor Awais, I have a question.
Okay.
Now, if we believe that this system may be implemented in real time, as far as I understand, this data collection is going into the cloud to make a decision making and then return back. Is that right?
Yes, but it is not in real time. It is in a planning stage. OD metrics usually used in
Okay.
the planning stage.
Okay. Okay.
So
So
we
you don't have a problem with end-to-end delay.
no, no,
Mhm.
we don't have because even our method take time to calculate. It used for planning the network. It can be
Okay.
for a network not constructed or a network will be expanded.
Mhm, 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 mhm. That's very clear. Thank you very much. Thank you very much. So I think I don't think we have more questions. So again, I would like to really appreciate the nice presentation and the great effort made by our esteemed speaker today, Professor Mahmoud Awais. Thank you very much for this nice presentation.
Thank you.
Thank you. So now we turn to have the second presentation. The second presentation will be with our second esteemed speaker today, Dr. Mandal. So please let me have the time to introduce Dr. Mandal for our respected audience. Dr. Mandal is a research staff at the instrumentation department in the Brickhaven National Laboratory in USA. Dr. Mandal is a former faculty member at the Case Western Reserve University at the University of Florida. He has more than 175 applications with 26 patents and a great list of awards, including but not limited to the President of India Golden Medal in 2002 and the MIT Doctoral Dissertation Award in 2009. I think Professor Iwis, if you would you please stop sharing from your side, and Dr. Mandal, I would appreciate if you can stop sharing the screen, please, Professor Iwis, and Dr. Mandal, I would appreciate if you can start sharing your presentation. I expect that Dr. Mandal will going to present for the next 30 minutes. Then we will have a room for question and answer. Whenever you have questions, please, just a reminder, you can write your questions in the chatting area whenever you have a question, and Dr. Mandal will do his best to answer all the questions by the end of the presentation. The floor is yours, Dr. Mandal, and looking forward for your interesting presentation.
Okay, so do you see the slides?
Yes, we can. You can just full screen, please.
Okay. I think I'm sharing the wrong screen. Hang on.
So
Okay, share.
we are now seeing the PowerPoint software
Yeah.
itself, not the full screen version.
Yeah, I think this should work now.
Yeah, now we are having the full screen window, so you can go ahead.
Okay. Let me just switch to the pointer. Okay. So thank you for attending, and thanks to the IEEE Census Council and Dr. Samif, particularly for inviting me to deliver this talk. So I'm really presenting this work on behalf of a bunch of colleagues, and some of whom are listed here. The main ones are listed here. As was mentioned, I'm at Brookhaven National Lab, which is one of the US Department of Energy national labs. We're located in Upton, which is a town about an hour east of New York City. And here I'm going to talk about our work, our recent work on AI hardware and algorithms. for radiation detectors. And you'll before that, before talking about our work in particular, I'll give you a bit of an overview about where I think AI is playing a big role in large-scale physics experiments in general, and then I'll focus more on our work. So the overview, like I said, we'll overview our work that really lies, I think, at the intersection of detectors, AI, and microelectronics. And in particular, you can see that we have overlaps between these areas. So where detectors and artificial intelligence overlap, we have the ability to do edge processing close to the sensor. Where we have microelectronics and detectors overlapping, we have this issue of scalability, like how do we actually scale detectors to large areas, large volumes, to collect as much data as we can for these large experiments. And where AI intersects microelectronics, the microelectronics feeds things like energy efficiency. So how do we make sure that the AI algorithms can live and function within this limited energy budget or power budget that we have for many of these systems? So therefore, we'll talk about how these various intersections all come together in this world of radiation detectors, which are one of the core areas which for large-scale experiments, because they're used to acquire data for experiments in particle physics, nuclear physics, photon science, basic energy science, and search for dark matter, rare event searches, and a bunch of other interesting physics applications. And what we'll see is that these techniques, the AI techniques that we'll discover, really let us do more efficient data processing close to the edge, close to the sensor, extract information so that instead of transmitting raw data, we are transmitting more meaningful information, which actually simplifies a lot of the processing that happens down the line. And in the process of doing this, we might need to use novel microelectronics technologies that go beyond normal CMOS based processing. We might use novel devices, we might use photonics and other types of technologies. So I'll briefly mention that. Also to mention that even though I'll focus really on our work with on large scale physics experiments, particularly colliders and rare event searches, the concepts we talk about really are more general than that, and you can apply them to other scientific use cases. Okay, so maybe I'll start off by doing an overview of where I think AI is really playing a role in large-scale physics. And really, I think AI is driving this kind of paradigm shift in how large experiments are designed and conducted. So the biggest challenge for these large experiments is the vast amount of data that they generate. So for example, the Large Hadron Collider and its forthcoming upgrade, which is the high luminosity LHC, the LHC, which is the Large Hadron Collider, is already generating a ton of data. The upgrade, which is the HL-LHC upgrade, which will be online in a few years, is going to produce exabytes of data annually. So exabyte is, I think it's 10 to the power 18 bits. So it's a huge amount of data. And this creates immense challenges for data acquisition, processing, and analysis. And now traditionally, data that was processed from data processing from these experiments relied on rule-based algorithms. Traditional rule-based algorithms where the rules were determined ahead of time, the algorithms were fixed, and you didn't really change them as the experiment progressed. But these algorithms are struggling to keep up with the complexity and scale of this, what we can call a data deluge. And so this is where artificial intelligence and machine learning, AI, ML has really become indispensable, I think, as a scientific tool. You can, by enabling these new capabilities across the entire experimental life cycle, really, from real-time data filtering close to the edge down to final physics analysis, offline. So at every stage of this processing, there are applications for AI and ML. And like I said, I think this really represents some sort of paradigm change, and we'll see more of it, not just for this sort of experiment, such as the particle collider, but so all sorts of other scientific applications as well. Now, in particularly focusing on physics applications, like I said, AI can be applied at every stage of the data processing pipeline. So starting from what we'd focus on today, near detector or edge AI. So these constitute very low latency, low power models that you have to run on custom chips, ASICs, application specific ICs, or on FPGAs, which are directly coupled to the sensors. And these perform low level tasks that have to be done quickly. So things like real time denoising, compression, detecting the occurrence of multiple events within a window, which is called pileup, and then rejecting those or correcting for them, classifying different pulse shapes, which are individual radiation events, into different shapes, different categories based on, for example, the category of particle that was that struck the sensor, the sort of particle identification, and so forth. And so these are all generally what I would call feature extraction tasks. And then once you have these features, you can actually provide some fast feedback to the sensor. For example, you can say, okay, these pixels are dead, don't consider data from them. Or maybe you're saturating some pixels, maybe you want to reduce their gain. These sorts of things, these very simple, fast feedback loops. Then the next level up in the chain, I would say, is what we call the real-time trigger or front-end trigger and reconstruction, or real-time reconstruction. So these are larger models that take the data that's being driven out from these near detector edge AI algorithms and process them further. And these are typically run on FPGAs and GPUs, and they're performing more complex real-time tasks. For example, low latency inference for doing particle identification. So, okay, initial level of identification might have happened even at the stage of the edge sensor. But the problem with the edge sensor is it only has access to local information. It doesn't have global context because it's, after all, near the sensor, and the sensor is huge. It has many, many layers and different types of sensors. So this is really the first stage where there's information available from the global experiment. So from a bunch of different sensors, or maybe a single sensor layer, but the whole sensor layer. And with this sort of larger context window that's available, the more complex algorithm that's running here on the FPGA GPU can perform better particle identification, with higher reliability and more precise identification. It can also do things like tracking, say which direction the particle came from, because it has access to a much larger data set from the entire sensor. It can also filter for events, remove noise, and make trigger decisions. So this part is important. The trigger decision here is the fact that even with existing sensors, and this is definitely going to be even more true for later sensors, there's already no way that people can process real-time data coming from the entire sensor without some sort of filtering, because there's just too much data being generated. It'd be computationally infeasible to store it all and process it all. And moreover, there is no need to do that, because most of the data that's actually being generated comes from expected physics outcomes. For example, there's a bunch of particle interactions in a collider that are always going to happen and are not of any great interest for the physics, because they are sort of background that you expect. You're really looking for some novel physics that is a new phenomenon that shows up in this very uninteresting background. So if you can detect this background, we can then remove it from our real-time data stream, which will compress it dramatically, and therefore the later processing stages only have to process the candidates that are of some interest rather than all this non-interesting background. So this sort of this decision is made by what's called a series of triggers. So traditionally, like I said before, these triggers, which are often classified as level 1 triggers, level 2 triggers, and so forth, were generally using very simple rule-based algorithms, because they have to run in real time. So to give you a sense of the scale, typical triggers have to operate within the, for a particle accelerator, have to operate within the time period of a single clock cycle for the beam clock, which for, let's say, the LHC is about 40 megahertz, which means they have to make the decision in 25 nanoseconds or less. So there was obviously no possibility of running anything very complicated, particularly given the processing capabilities that were present in the past. But with the increasing availability of high-powered FPGAs and GPUs, you can think about actually doing more complicated operations even within this very short 40 nanosecond window. So now we can incorporate more complicated AI within these within this very strict latency window. So that would be the second level of AI being applied. And the third thing is, once the filter data has been processed and has been processed by the second layer, it can then go into the so-called counting room where it's stored and then can be processed offline. So this can really use very large scale models. So here, the third step, we can use very large scale deep learning models. There's no really big constraint on latency anymore. So now you can have much larger models. Graph neural networks are used, transformers, generative models, and these can run on large clusters, HPC clusters, and these can perform even higher level physics tasks, reconstructing complete events, detecting anomalies, extracting rare signatures, and generating new physics. The final thing I'd like to mention here is, apart from all these, which are really all these three stages that I talked about, which are in the data acquisition pipeline, there is also the idea of using AI for controlling the entire experiment and making it more autonomous. So here, you can think of this as being an application of agentic AI type principles, where there's an AI agent which is using something like reinforcement learning typically or Bayesian optimization to do AI-driven control. And this is really important because many of these experiments are quite complicated. There are many different types of controls. For example, there's beam alignment controls in a collider that have to be handled in real time. There are many sensors with different gains, and they have to be you have to allocate them efficiently. You have to tune various energy levels of the beam and its position in real time. And these are all getting so complicated that it was that for a human to do it was taking a long time, and maybe the solution they were finding was not the best or most efficient or more optimal solution. So here again is a perfect example of where now you can use an AI tool to actually automate the process of making the experiment better and more tuned to get the best possible physics outcomes. Particularly important actually because these experiments are so large that they're very expensive to run. So if you can most efficiently utilize the amount of experimental time available, then you're saving large amounts of money, which can then be used to do more physics and get more results in the limited amount of time that you have to run the experiment. So this is all very good also from an economic point of view. Okay, so this kind of what I was talking about on the previous slide is kind of graphically summarized here. So really what I would like to say here is these are the different steps, all the way from the left, which is at the level of the sensor itself. And here people are actually using AI. I didn't talk about this, but people are actually using AI to design the sensors, optimize them to the level of actually device design or sensor design, where they're running simulations with neural network models to improve the design of the sensors themselves, to what we'll talk about here really, which is edge processing on the detector, to real-time processing, which I may talk about the high-level trigger, and then the offline reconstruction analysis. And then finally, we get the physics results. And then sitting below all this is the AI for automation and control, which might be using reinforcement learning to control the overall collider. So again, so this gives you kind of a global picture of where AI fits in, and hopefully that was of interest. But now, given the short time that I have really in this talk, I'll focus on the edge AI and how we have been contributing to it, and again in the context of these sorts of experiments. Okay, so why edge AI for radiation detectors? Again, I mentioned the data deluge at the source. We are getting a huge amount of data from things like modern silicon vertex trackers, which are basically giant cameras that track charged particles or high energy particles in general. We have scintillators, which are basically sensors where incoming particle generates light, and then the light is detected by another second sensor, which is a photodetector. So basically a transducer followed by a detector. And then things like time projection chambers, which are designed to track charged particles, also called TPCs. Many of them inside liquid argon, hence liquid argon TPCs are large TPCs. Things like that, they all generate quite a lot of data. So as I said, it's becoming impractical to stream them losslessly. So we want to extract important features from them and then stream the features, not the raw data. Now, however, while doing this, you have to meet strict latency and power budgets. So, typically your latencies are in the nanoseconds to maybe a few microseconds range, depending on the experiment, and depending on also the type of sensor, your entire AI algorithm might have to fit within the power budget of a few hundred microwatt to maybe a couple of milliwatt, depending on the experiment and the sensor. So in order to keep, therefore, the size of the model within bound, you have to utilize techniques like quantization and pruning to keep the network size in bound and reduce the number of weights, play all these tricks. And then it also helps to use co-design principles where you try to design the hardware along with the model. And I'll talk about an example of that. This typically means designing the system either using an application-specific IC, an ASIC, or an FPGA. And then finally, like I said, this has to be all done under the strict power, area, latency constraints. But in addition to that, many of these detectors also have to sit quite close to the beam for a particle detector or particle collider. And that's a very high radiation environment with lots of nasty high energy particles flying around. So you have to utilize radiation tolerant design principles. So there are well-known principles for making a circuits more tolerant to radiation, both at the design level, radiation hardness by design, and also at the implementation level, but you have to implement those. So this gives you another kind of layer of complexity. Okay, so maybe I'll just briefly mention the types of sensors we're talking about. So these are either strip sensors. You have long strips of semiconductor, doped semiconductor, which form individual, each of these individual sensors, or sometimes you have pixels, which could be rectangular arrays or hexagonal arrays. So you can think of these as basically basically very sophisticated large-scale cameras, actually quite similar technology in many cases to the ones you have inside your cell phones, just utilized for a scientific application instead of consumer imaging. And these can be assembled in various ways. So sometimes you have monolithic sensors. That's the one in the middle here, where everything is actually integrated on one chip. That's actually the closest to a traditional, let's say, CMOS type sensor that you would find inside a phone or other device. But on the other hand, sometimes you have sensors which have other types of materials deposited on them, where the electronics are maybe normal CMOS, where there is some non-CMOS layer, which is the sensor deposited on top. And this is what we call a hybrid integration. These days, there's also focus on 3D stacking, where you have multiple dies. Maybe some of them are the sensor layers, but also multiple circuit dies. Maybe one of them has analog circuits on it, and then the one below that might have some of the AI components on them, vertically integrated using through silicon vias or using direct die-to-die connections. So this is also something that's being worked on at the moment. But regardless of the type of integration, ultimately these detect these, I would say, readout chips, which might have your AI front-end algorithm or AI that have the front ends on them, and also the edge AI system on them. These are deployed all over various types of experiments. So, for example, in high energy physics, in nuclear physics, in astrophysics, in basic photon science, X-ray detectors. So there are chips, readout chips everywhere. For example, you can see here in this nuclear physics application, you have this cylindrical sensor layer, which is actually wrapped around the beam pipe where the beam is going through. And this is actually thinned down silicon wafer, entire wafer, so wafer level sensor. This is actually what is being developed for the ALICE experiment at CERN, and also the Electron Ion Collider at BNL, which is where I work. So these sorts of systems, you can see, have a lot of complexity in them in terms of the front end design. But now we're talking about actually adding more intelligence to them. And this is where the edge AI application comes in. So let's just talk briefly about, just to put this into context, what each of these sensors might look like. So I told you about the physical construction of the sensor. So after that, the readout chain really starts off with a very pretty simple charge amplifier, and then some sort of circuit to optimize the response. It's called a pole zero cancellation network, and then typically some sort of shaping filter that takes the brief charge packet. So every charge particle that interacts with the sensor will create a charge packet. That packet will, you can think of looking like a delta function in time, so a very brief pulse. That actually gets filtered by the frequency responses of our various components in this chain, particularly the shaping filter at the end, until we get these pulses. So you can think of each event as or each charge particle generating one pulse. So the difference you should think about compared to, let's say, an optical detector that might be in your cell phone is that that typically operates in an integrating mode, where you're looking at the sum effect at any given time of hundreds or thousands of photons. In this case, since the particles we are considering, which might be photons like X-rays or gamma rays, or could be other heavy particles, these have much more energy. So in fact, the amount of charge they generate, which might be thousands of electrons, is large enough, or holes. They could be typically large enough that you can actually detect individual ones. So we can actually count individual particles and actually get details about their, for example, energy by looking at how tall the pulse is, or some details about the type of particle by looking at the shape of the pulse. So that information is available, which is not there in an integrating type sensor, because there you're just looking at the summed effect of a whole bunch of individual events. Yeah, so like I said, the types of measurements we do, and this is what we might have the neural network, our on-chip AI front-end edge AI system actually detect. There could be various types of measurements that we can try to do and extract information from. So instead of, let me back up for a second. The kind of the default method that people use now is to just either threshold these events and just transmit a 1-bit pulse saying that a pulse was actually detected. So this would be called a thresholding type detector. Or you actually have an EDC and you digitize the entire shape and send out individual points which correspond to the shape of the pulse. And then this can be processed later. So the neither of this is optimal, in the sense, if you have a threshold detector, yes, you can detect events, but then you lose all other information about the event. You don't know you don't know what sort of energy level the pulse had. You don't know what type of pulse it was. So all that information is lost. Whereas if you have an ADC and you digitize at high resolution and transmit that, yes, now you have retained all that information, but you have a ton of information then to transmit, because it's, say, multiple bits per point and then at least several points per waveform. So you can easily see that this will take a lot of data. So the question is, can we get the best of both worlds? And this is where the neural net might help us, because it can try and replicate some of the later types of processing applications that are now done offline, or at least later down in the processing chain, and do them inside the front end, and transmit only the results of those measurements rather than the raw waveforms. So first of these measurements is amplitude, right, which is essentially proportional to energy. Then this has to deal with the precision of this has to deal with, of course, noise in the front end and the error that happens because of the finite digitization time, which is the period between digitization points. The next thing we can do is compensate for what we call charge sharing. So this is actually an interesting effect, where this is an effect that arises from the fact that you have a pixelated detector, or maybe either 1D or 2D, and your particles can appear anywhere. So, they don't have to necessarily land at the center of each of your pixels, right? They can happen in the middle. And then what will happen is the charge will be generated not at one pixel, but actually at several pixels. So now you have this problem, because you have several pixels actually giving you pulses, and if you digitize them and then decide actually where did the particle hit. So there are actually algorithms which you can see could be not very difficult. You can, for example, look at where the charges are non-zero and then calculate something like a centroid, and then say that's actually where the particle hit. So these sorts of operations are possible, and people have devised algorithms for them, but they were traditionally performed offline. What if a neural net could run this in real time? Then it could actually report the centroid directly instead of having to report the amplitudes of each of these individual pixels, which would be a lot of data compression. You can also measure time of arrival, so TOA. That's actually important. For example, you can use this to track the direction of particles. And this is actually quite a difficult problem, because traditionally, like I said, remember, we traditionally detect these events by thresholding them. The problem is the pulse amplitude changes. So depending on where you set the threshold, you can see that if you have a small pulse, it'll cross the threshold later than if you have a large pulse, because the large pulse will have a high initial slope compared to the small pulse. And therefore, you'll get with this problem, which is called time walk, which means the time at which you cross the threshold depends on how big the pulse is. So to correct that, you can do other tricks, like you can detect not just where the pulse started, but also where it goes below the threshold. This is called a time over threshold measurement. And by combining this time over threshold measurement with this arrival time or leading edge discrimination measurement, you can actually compress the variability you have in the pulse. But yeah, still these applications were again typically done using specialized circuits, which are not very flexible, or they were done offline on the digitized data. What if a neural net could kind of efficiently do these operations? Then it can send these features out instead of, again, the raw data. Yeah, so this is another type of discriminator called constant fraction discrimination. I'll skip this in interest of time, but it's the same sort of idea. It's another type of measurement you can do on the pulse. And the last one I'd like to mention here is pulse shape analysis, which gives you actually quite a bit of interesting information in some experiments. Because, for example, a classical problem in this context is how to separate out one type of unwanted particle and only retain particles that are of interest. For example, in many experiments, neutrons and gamma rays are often confused. So if you can have, these types of but neutrons and gammas often result in slightly different pulse shapes in a given detector. So if you can then take this pulse shape and then say, okay, this is a neutron type shape versus a gamma type shape, then you can toss out the one you don't care about and only retain the ones you want. So a neural net might be ideally suited for this sort of application, because again, it's a multidimensional problem. You have many points typically acquired per pulse shape, and then you have to make a decision based on this. So it's a simple classification problem for a neural net, but it would be it would potentially again lead to a large amount of data compression, because, for example, the unwanted type of particle might be a lot of what you actually detect, and then you can throw it away using this procedure without compromising your physics, thereby reducing the data rate. Yeah, so basically, I hope I've been through this series of examples or types of measurements. I think I've hopefully motivated the need for some sort of edge processing. And now we'll talk about really how this might be implemented. So when we try to do this, the procedure we came up with for, well, first of all, let me back up. First of all, we tried different types of algorithms. So we said, okay, we shouldn't really start off with neural nets as the default. Let's think of some classical algorithms that we could use. Adaptive filters. After all, neural net essentially implements some sort of adaptive filter and approximation algorithm. So what if you implement something like that? Or if you do a function minimization using a variety of traditionally well-known function minimization methods. So what we found was that for the problems that we were considering, which are actually from a data science perspective not very complicated, we have relatively small a small number of features that we're trying to extract from a small number of points, let's say 10 or 20 points per pulse. We found that a lot of the algorithms actually performed similarly, but the ANN, artificial neural net, has the big advantage that it's actually really efficient to implement in hardware compared to a lot of other algorithms. So let's say you try to do a traditional function minimization using, let's say, mean square error or some other metric, you'll find you need to do matrix inversions, a lot of multiplies. It gets to be computationally quite intensive. Neural net can be trained to do the same operation. And after training, it's just as good at that operation as any of these classical algorithms. On the other hand, all you need to implement a traditional feed-forward net is some matrix vector multiplications and a nonlinearity, which can be implemented very efficiently. For example, if it's a ReLU or other efficient nonlinearity like that. So from a hardware point of view, actually, even though a neural net has to be trained and you have to store the weight somewhere, it actually ends up being much more efficient in many cases than these classical algorithms because of the hardware structure. And that's really what we found. But then we still have this issue of weight storage, which, given that we have limited area and power power available in our front-end chips, is going to be a problem. So we need to really utilize all the techniques we can to minimize the size of the network. And this is, of course, the general problem of quantization-aware training or pruning and these sorts of techniques for compressing the size of the model. In general, this reduces to this problem of picking hyperparameters efficiently. The problem is that there are many, many, many hyperparameters. So you can give you an example. Let's say we just consider this simple problem where there's 1 to 3 hidden layers. If we just pick the network, say it's an MLP, but even then with only up to 3 hidden layers and let's say up to 16 perceptrons per layer, and then we still have to decide on how many bits we need to assign to each of the weights. We still have to decide how many bits to assign to the output weights, and also what sort of synthesis we use to convert this to a circuit form. We find we end up with a humongous number of possible choices for these hyperparameters, a very large number. So we need an efficient way to search through this space to come up with an efficient implementation that can fit inside our framework, inside our constraints. So this is really what we've been doing. We've developed this procedure which utilizes multi-objective Bayesian optimization to develop these and find these Pareto optimal neural net solutions. So I'll spend a few minutes talking about this. Okay, so the existing method that people have developed, and this has been published a few years ago, is based on taking something like a normal model, say a TensorFlow model in Keras, going through this layer called Q-Keras, which is quantized Keras, and this actually tries to quantize the network, find out the optimal values of these hyperparameters under some constraints. But the issue with this is it doesn't have good models for the hardware constraints. It uses some theoretical estimates for things like power and area and how they scale with the implementation. So these theoretical models are good, but they're not very accurate because they ignore a lot of the circuit complexity. So that limits the accuracy with which you can actually model the behavior of the ultimate circuit that comes out of this quantization procedure. And this has been implemented in various packages. For example, this quite well-known package called HLS4ML, which is kind of widely used these days by the physics community for implementing neural nets on FPGAs. So what we came up with actually was to incorporate logic synthesis within this pipeline, so we get a much better idea of the performance of the actual circuit once it's implementing the model than relying on these theoretical estimates. And this is what so therefore, essentially, we've expanded the design space some more because we also include, for example, various choices on how to perform the logic synthesis, which further leads to this very giant design space, even for a fairly simple problem such as this. And so, yeah, so we included logic synthesis in the pipeline. So we used open source tools for this. What has really been quite nice here is that Google a few years ago partnered with a foundry called Skywater to launch one of the, I think the first open source PDK, process development kit for integrated circuits. This is a 130 nanometer process from Skywater. And this lets us actually run this with entirely open source tools. It's very convenient because you don't have to it makes it very easy to share our work with others and collaborate with other institutes. Yeah, then we run our multi-parameter Bayesian optimization, which is actually a standard toolkit called Optuna, which has just been adapted to this problem. We move on with this, and we integrated everything nicely. We containerized everything, and then we ran it. So it's a nice integrated framework. So it's nice and extensible, configurable to this complete pipeline. So we call this really a kind of co-design, I would say, because the AI algorithm is being co-designed with the chip implementation. Ultimately, we come up with these Pareto optimal recommendations for what the designer might finally implement on chip. Yeah, so here are some performance examples. So we fed the in order to find the optimal network, we created some synthetic data sets. We also have experimental data sets that look similar, but essentially this is the axis here is the data index, and the axis perpendicular to is actual shape of the pulse. You can see it's a pulse-like shape that's kind of roughly aligned in the middle, but not perfectly because there's noise in the system. The signal to noise ratio here is varying between 1 and 20. The peak signal to noise, so the peak amplitude divided by the RMS noise level. And it's downsampled to only about 9 points per window to keep the processing requirements reasonable. We can sample faster, but then just means the networks get bigger. So we're really constrained by that. So yeah, so with that, we can efficiently, our procedure actually, this is after 22,000 of these logic synthesis and training runs, we can efficiently estimate the hypervolume. So the hypervolume being searched increases quite nicely as a function of the trial number. And we also, you can see this graph here is the distance between points on this Pareto optimal front. That's shrinking, which means actually finding these solutions more efficiently. And yeah, you can see the structure of this Pareto front in this three-dimensional space. Validation loss is a measure of performance. Delay is a measure of circuit efficiency, so lower delay is better. And power obviously is another measure of circuit efficiency, so lower power is better. And so points that are on this Pareto front are a good compromise between these three kind of competing objectives, right? And that's really the beauty of the Bayesian optimizer. It lets you pick good compromises when you have competing objectives in the optimization. Yeah, and then when you put this together, we come up with a family of neural networks. So what I wanted to show here is these are color-coded by the average number of quantized bits and also the number of layers. So you can see this is a weighted view of this neural network architecture. You can see it's interesting. The network tends to, the optimizer tends to prefer networks which have high quantization depths, which means actually 6 more bits devoted to the first layer. And it prefers to have very shallow second layers and also very shallow third layers, but it also wants high quantizations on the third layer. So whereas the other layers here, you can see it really doesn't want them. They get devoted very few bits, and you can dispense with them actually entirely. Many of the solutions only have 2 or 3 layers depths. So this is really telling us for this problem, we don't need anything more than, let's say, 2 or 3 layers. And also we only need a small number of neurons for the later layers, but they do have to be quantized to 5 or 6 bits of precision. So in this particular example, we picked about 8 bits for the actual implementation in hardware. And is this any better than the traditional method? Actually, it is, because you can see here, this graph line here is how much of the hypervolume is being exposed, is being searched by when you use the theory-based method I talked about before. Whereas when you incorporate logic synthesis, you actually explore the volume more efficiently, and you generate a lot more Pareto optimal solutions. So QKRS is the theoretical method. You only get the blue points. Our method produces a lot more points on this Pareto optimal front. So you have a lot more choice when you pick the actual network you want to implement. Okay, and so the final point, yeah, we put this together finally in a chip, which is our first chip with the integrated machine learning in the backend. So we're excited about this. So it's got it's a 1D array of 23 channels on this chip. It's 5 millimeters by 5 millimeters in 65 nanometer CMOS. So we have the front ends and ADCs, which are traditional designs, but then we have a large, an efficient DSP block, which extracts these features, makes these 9-point windows that I mentioned, which are what are then fed into a machine learning block, which is our multi-layered MLP. Just the design of the MLP, we used all the weights. I mean, all the weights are stored locally on chip. We managed to do that. Also, we put in stochastic rounding, which is a well-known technique that allows you to do in situ training even with low resolution weights. It's 8 bits in our case. Net result is we can run the whole thing, the entire channel, with about 10 milliwatts of power, which is reasonable. It's within sort of traditional power budgets for this type of detector. Okay, and this is the overall design of the chip, but I think I'm probably out of time, so let me stop here. I'll just briefly mention two more things. We're also working on actually readout, which gives us some more interesting AI opportunities, because you can do event-based readout, which is asynchronous readout, and then process them using this kind of neuromorphic analogy using spiky neural nets. So this is something we've started working on. This actually has the advantage that you can do the processing slightly off detect and not really on the sensor itself, because even though I said you can fit a neural net within a front-end ASIC, it still occupies some of the area that could be utilized for example, detecting light, right, instead of processing. So if you can push some of that off close to the sensor, but a little bit away from it, or maybe 3D integrated with it, this would be great. So this event-based link, which is similar to, let's say, conceptually similar to an optical nerve between the eye and the brain, going into a spiky neural net that's just sitting below the sensor. We think this is really a good way out of this compromise, and this is what we are working on. One of the things we're working on at the moment. Yep, we're also looking at novel devices, including maybe going beyond CMOS with some of these RRAMs, implementing them. But this is very early work, so I'll just skip this. And finally, also incorporating photonics, particularly for data transmission, because photonics are very efficient at transmitting data particularly at long distances. So I think, again, incorporating integrated photonics into these edge AI systems has lots of energy efficiency benefits. And we are again looking at that as part of a new project. Yep. So that's so maybe I'll just stop here and say, yeah, I've introduced some of the major themes of our current work, and really they're all focused on tackling this data deluge problem for current and next generation detectors by using specialized on or near detector AI-based edge processing, sometimes on commodity hardware, sometimes on custom hardware. But really the objective being to improve data quality and detector performance, give us new physics in a shorter period of time. And this leverages new microelectronics, heterogeneous integration, things like integrated photonics and beyond CMOS as well. And final point is these developments all need what we call co-design. So we have to work closely with the device designers, with the circuit designers, with the AI algorithm designers, and kind of work together to make this work, because it's really a multidimensional effort. Yeah, thank you, and happy to take questions. And yeah, if you have any thoughts on working together, feel free to reach out and we can discuss. Thank you.
Thank you very much. It's really a very nice presentation. Thank you very much, Dr. Mandal, for sharing these challenging and interesting, let me say, story with hardware AI-based detectors. So let me now open the door for questions. If anyone have a question, please just raise your hand if there is any questions. I can see okay, I cannot see questions in the chat room, and I also cannot see, but personally, I can make use that we still have 5 minutes to the end of the presentation. So if you permit me, Dr. Mandal, I have one or two quick questions. First, I would like to ask about you mentioned the challenges related to integrating AI in hardware, and this is your main focus. But do you believe that the challenges just can impact the cost of making such a detectors will enable having such a technology to be commercial soon?
So I think we are benefiting from advances in commercial technology. So, the process scaling that's being driven by commercial applications, we eventually can use them for our designs. And for example, new processors have integrated RRAM on them, which can be used for efficient multiplications, matrix vector multiplies. This is something that has been driven by industry, but we are getting access to these. So I would say it's really the reverse. We are benefiting from commercial developments in AI and hardware for AI. And we're just utilizing them for our scientific purposes, which is a good thing because it's very, I would say it's beyond our capabilities to develop new technology because they're so expensive. But the good thing is since AI is progressing so fast, new technologies are being developed for commercial applications, and we can utilize them.
Okay.
Yeah.
Okay, I have one more question, if you permit me. You mentioned that for the case you mentioned, you use, I think, 3 layers for the ANN model, if I remember correctly.
Yeah.
And you mentioned that this is sufficient in the case of this detector. Now, one of the advantages of using ANN or any machine learning model over, or sorry, any AI model over cloud is that we can have a dynamic tool that can adapt based on the type of the problem. Now with the hardware, I believe this will make some sort of restriction because now you design your chip with a 3 layered, and this is not no longer dynamic. Is this right?
So yes, the model is not dynamic anymore, but I mean the weights are still programmable. So I think what we were showing was for a few different measurements that we wanted to make. For example, pulse amplitude, pulse width, things like that. They could all be computed by this network. So and of course you can retrain the weights because we have control over that. So so in that sense, it's flexible, but of course you cannot change. Once it's in an ASIC, you cannot change the number of layers or the number of neurons per layer, but you can still change the weights. So that, yeah.
I can understand. Okay, so thank you very much for the presentation again.
Okay,
It's really
thank
a
you.
very nice presentation. Personally, I got benefit a lot from having this big opportunity to be one of your audience today. Thank you very much for this
Thank
presentation.
you.
And of
Thank you.
course, thank you for all our respected attendees for this presentation. I think by that we are concluding our 5th webinar for the IEEE Egypt Sensor chapter. Thank you very much for your respected attendance. The session has been recorded, so please feel free to email me if you need for some reason the recording of the session. And also for our respected speakers, I'm going to share with you the link
Thank
for
you, Dr.
the
Sami. Thank you.
yeah, thank you very much, Dr. Mahmoud. I'm going to share with you the link for the recording. So
I'm
please
waiting
feel
for
free
it, inshallah.
to share it among your students as well as your network. Again, thank you very much for your participation. It was really a very nice opportunity having 2 prestigious speakers with us today. Thank you. And looking forward for another opportunity, maybe in the next time. Dr.
Inshallah.
Mahmoud, we're going to invite us into a suit, a very nice suit,
Inshallah,
by the way. So we
Have a
or
good
maybe Dr.
campus.
Mandal in US. So thank you very
US,
much
we
for
want
that.
US.
Yeah.
Dr. Mandel
So
will
thank you
invite
very much.
أصلا إن شاء الله يعني.
Yeah. So thank you very much for that, and looking forward for a next webinar. Thank you.
Thank you.
Bye-bye.
Bye.
Bye.
Bye-bye.